Good day, friends. Today we're going to discuss about the ray optics. If you remember last time we have discussed about the nature of light, and we have said that light can behave as an electromagnetic wave, disturbance in the electromagnetic field, and also it can behave as a particle of light, which is called photon, doesn't have any rest mass, and moves in the speed of light, which is 300,000 kilometers per second, kilometers per second, which is 3 multiplied 10 to the power of 8 meters per second, Okay, but also we have said that it has one more nature, which is this one, ray, but we have also noted that ray is not an actual nature of it. Instead, it's an ability, it's a mathematical abstraction, it's some characteristics, let's better say it, that light can travel just in straight lines, and this is the main principle that we're going to work with today. Light can travel in straight lines. Okay, mostly today we're going to concentrate on optical elements, which are the lenses, which refract light, and also mirrors which reflect light. Okay, let's talk about them. Basically, we have mirrors in everywhere in our daily life. Maybe even in your rooms you have mirrors. And what about lenses? Lenses are more familiar to people who wear glasses, because basically that's what lenses are. They refract light, and we're going to talk about it later, maybe in other videos, how we can correct our vision, those people who have bad eyesight, let's say. And basically there are two types of spherical lenses. Exactly spherical one, and we're going to talk about why do we call them exactly spherical ones. Lenses can be also plane lenses. For example, even the glass of your window can be considered as a lens, but it's just plain. Okay, it's just plain. What about the spherical thin lenses? Thin, it's really important. Why thin? I will tell you about this a little bit later, but let's concentrate on these two, converging lens and diverging lens. Okay, converging lens, or we also call it convex lens. Diverging lens is also called concave lens. Converging lens, what does it do? For example, let's talk about only two parallel rays. Parallel rays. Not some this kind of angles, but straight parallel rays. And it will be collected at a certain point, which is called this point, focal point. And distance from the lens to that focal point is called focal length. Okay. And as I have said, we are going to tell you why it is called thin, because in real life the lens wouldn't look like this. It is in fact something very, very, very narrow, but if you close it up, if you zoom in, it will look to you that it's also spherical. Okay, why is it spherical? Because if I take this converging lens, and if I draw it again here, for example, then if I continue to draw it here, for example, some imaginary continuation of this image, then you can see that it is two spheres, right? And if it is sphere, then definitely it has some central point, and distance to that central point is just radius as general. But as you can see, as you can notice, exactly at that half of that radius is our focal point, and here as well. You can see that it's not this one, it's not this close one. No, instead it is this far one. Why? Because this one, this whole thing, is one part. That's why it would be this thing, focal length, not this closer part. And also the same thing goes for here. It's not that closer part, not this one, but we're going to continue it here because this is the full sphere, right? Okay, good. I hope you understand it. Let's talk about diverging lens, or we also call it concave lens. Diverging lens, again, two parallel rays, they go to the lens and they diverge, they refract outward. But the main question is, why exactly like this? Because this one is also the light that spreads outwards. This one is also light that spreads outwards. What about this one or this one? Well, this is straight, but a little bit some angle, some small angle probably, or instead something a very large angle. Why not this kind of? Well, basically because they also concentrate and they also work with focal point, and as you can see, they go outward, they run away from that focal point, and that's why we need to remember that converging lens, they collect light at one point. That's why their focal point would be positive. And as you can see, as in this image, it will have two focal points, and both of them would be positive, because anyway, if you put object right here, if you put object right here, anyway, both of those points will collect light. They will collect light. And here they would spread it outward. That's why they do not collect. Instead, they run away from that focal point. That's why it would be minus. And the same thing, let's go here. If you continue, if I take this image of diverging lens, and if I continue it here, you can see that it's again two spheres. Again, central point, the radius is right here again, and exactly at that half of the radius, this is our focal point, but this distance is focal length. Okay, I hope that you can understand it. Okay, lenses, they refract light, which means that they just let light to get through them. They just bend light, not like a metal. For example, let's imagine this kind of light ray. They do not bend it, for example, like this, like the metal. No, they just change their direction, better to say it. Okay. But the main thing is that they let light through with changing its direction. But when we talk about concave mirror, they also change their direction, but they don't let light through. That's why it is reflection. we have two types of mirrors, which are also spherical mirrors. Yeah, we can have our plane mirrors that we have in our daily life at your rooms, for example, and but there might be other types of mirrors, which are these two: concave mirrors and convex mirrors. Concave mirrors are something very close to the converging lens because they also converge light to one point, and that point is exactly what our focal point is. Whereas convex mirror, they just refract or reflect light outward, not inward, right? You can see that it goes here and then it spreads outwards, right, like this. And also, as you can see here, they go away from the focal point. That's why for convex mirror it would be minus, for concave mirror it would be plus, it would be positive. Okay, I hope that you understand it. Let's look at this again. Okay, some people looking here, they might say, oh, here I can see two spheres as well. But no, instead, we don't write here two lenses. You might say, well, we have this part. Why don't we draw here some other, the second lens like this? I can see it. Yes, but we are drawing it like this only to make its thickness, not to say that it can have some second part like this. Yeah, okay. The main principle is this part because it does not let light through anyway. It does not interact with this part of the mirror. Okay, the same thing goes for this one. As you can see, it goes here and reflects outwards. Yeah, it does not go inside and then outwards. No, instead it meets the first face of that mirror and then just goes out already. It does not interact with this part. That's why you can see here that it does not have continuation with this part. Yeah, it's not the second sphere, it's just one sphere, and it's the near part because light interacts with only the near part of it. Okay, again, central point, focal length, and double of that focal length is the radius. Okay, good. I hope it's pretty intuitive to you. Let's move on. Yeah, as I have told you, focal point is exactly the half of the radius anyway. A specific spot where parallel lines of light meet after passing through lens or mirror. Okay, this is very important thing. As I have said, this is really important to talk about the parallel rays. Yeah, for example, if this is a parallel ray, this one is parallel ray. Yeah, two parallel rays which are straight horizontally. Only those ones will concentrate on focal point. Yeah, they would go away or go into the focal point, but not the others. Yeah, for example, if we have some long object, for example, let's imagine maybe something like this, which is line, for example, and if this small object, yeah, let's say it does not have much of the height, instead it's something long, and we have some light going here and light go from the far side. This far side, it's easy to bend, that's why it will collect near, and this closer side, it would bend a little bit less. Why? If you have a question, this one is small angle, as you can see, this is larger angle, and if this is, for example, if you have one more light like this, yet the same point, maybe this point again, the same point here, it's harder to collect. That's why they will collect in different points, not on the focal point. Okay, that's really important. Only parallel rays. Okay. 3 rules of ray tracing. Right now, we're going to talk about ray tracing. Basically, we'll learn how to draw them. And the rule number 1 goes like this. Light going straight passes through the focal point. Yeah. For example, you have any object like this. Yeah. For example, this kind of object. And you can draw as many rays as you want. Yeah. It can go like this. It can go like this. In fact, we say it's all directions. It can also go like this, and so on and so on and so on. But to not complicate, it's enough for us to write down just 3 of them. Yeah. And it's sometimes enough to work with only 2 of them. Yeah, so the third one is always extra. Yeah, for example, if we can not see any cross of 2 lines, then of course we add the third one. But if you can see that at a certain point 2 lines cross with each other, then you can definitely say that the third one will also pass through that point. Okay. The first one, light going straight passes through the focal point. Okay, as you can see, this one. This is our converging lens, yeah? Okay, what is this thing? For example, look at this. It does not remind us something like this about the converging lens. To work with it further, let me talk about this one, yeah? This is very important. Further, when we work with converging lenses, yeah, diverging lenses, concave, convex mirrors, then we will draw them like this because they are thin, as I have said. This is just for exaggerating, yeah, it's just so it was visible. In fact, this is thin spherical. In fact, it's something like this. It's still spherical because if you continue it, it's something very large sphere. In fact, the same thing goes here and so on. Okay, okay, we'll draw them as this kind of arrow, but inward. Yeah, no, well, outward. Yeah, basically you can see that you can continue this line like this, yeah, and they collect light. This thing will collect light to a certain point, or if it is said that it is the mirror, it would collect inside, like this kind of. Yep. Okay. And because basically they play the very same function. The very same thing goes for diverging lens and convex mirrors. They diverge light. It lets light through, but it goes outside. But the same thing happens in convex mirrors. Only distinction is that they do not let light through. They also diverge it, but not letting light through. They just reflect it. Okay. And we will draw them as this one. In fact, it's very convenient. Why? Because we can continue lines with this one and continue connect these 2 parts, and you will have this image of diverging lens. Okay, yeah, good. I hope that you understand it. You can remember it. Yeah. Okay. this is our converging lens. This is our converging lens. Then, well, this is our first rule. Light going straight passes through focal point. Well, let's draw it. First line which goes straight, it passes through focal point, which is this our point. Okay. The second one, light passing through the focal point, it goes straight. Okay. We can draw many lines, as I have said. It does not have to go at some point. It goes everywhere. But let's choose the second one, which goes from near focal point. Then it just goes straight. Yeah. As you can see, it's one more ray, and as you can see, not all of them collect at focal point. So focal point is not about collecting all the light. No, only parallel, straight lights, which are horizontal, for example. Yeah. Or goes just in one axis. Yeah. Okay. And the third one, you can see here two rules, but in fact it's the same rule, but one of them for mirrors, one of them for lenses. Okay, light passing through C, which is the center of the lens, yeah, this one, does not bend. As you can see, it just passes through as a straight thing. And as you can see, using these three rules, the light going straight goes through focal point, this one, yeah. The light which goes from this focal point, it goes straight, yeah. It's really easy to remember. And as I have said, you need only two lines to cross, and as you can see, at that point you will have your image. This will be your image. And as I have said, if you find this cross between two points or between two lines, then your third line will definitely pass through it. And as you can see, it does like this. Okay, yeah, okay. But you can use, maybe you don't have to use this one because you can achieve it with two lines. You don't have to draw this one, or maybe you don't have to draw this one. Maybe just you'll need two of them. But sometimes there are cases when we cannot just use two. We cannot use just two lines because they don't cross with each other. Okay, okay. And for mirrors, it goes like this. Light going through center of a mirror reflects the same angle. So basically, it's the law of reflection is like this. Angle of incidence goes like angle of reflection. Yeah. If it was converging or a concave mirror, yeah. If it was concave mirror, then what would happen? Light going straight, it converges inside. Yeah. It does not go through. The light which goes through, it would go straight. Yeah, like this. The same rule. And the third one, which goes to the center of the mirror, it reflects the same angle. And as you can see, our image would happen here, yeah? So you remember this one and this one, the same angle. This angle and this angle have to be the same. Okay, good. I hope that you understand it. We have here a formula to calculate it. We have this kind of formula, which is 1 divided by F equals 1 divided by DO plus 1 divided by DI. Basically, some people write it as S, this is S prime. Some books write it maybe something like this is large F, this is small f, or this is D, this is smaller f, yeah, something like this. But for convenience, I will use this one. Why? Because f is a focal length. It's just one f. You don't have to mess this up. Yeah, distance from the focal point to the lens. You have some lens and your focal point, and distance from that focal point to the lens is your focal length. Yeah, like this. Okay, good. DO just says the distance of the object. It's pretty convenient. Distance of the object to the lens or the mirror. Yeah, we have some lens, converging lens, and our object, and that whole distance would be our DO. And DI is the distance of the image to the lens or the mirror. Yeah, as you can see here, we have the main object. This whole thing is our distance of the object, and this whole part is the distance of the image. This is our image where it would appear. Okay, good. Okay, I hope that is pretty good. But also let's talk about this one, image characteristics. Okay, image characteristics. Images can be upright. Yeah, if our object stands like this one. Yeah, upright. Then our image can be also upright, but it can also be inverted like this. It can be, for example, in our case, you can see that it's inverted. Okay, good. And if upright, we have one more thing called magnification. We're going to talk about it a little bit later. Let's now concentrate on magnified and demagnified. Magnification is about enlargement or getting shorter. As you can see, our object here is larger than our image. Yeah, because it's one full box, and here it's not the full box because it's here. Yeah. Okay, it's definitely shortened, which means that it's demagnified. Yeah, it magnified, it got shorter. Yeah, and the third one is that it's real or it's virtual. It's virtual. Yeah, what about real and virtual? Well, as you can see, if the true lines like this in converging lens, yeah, these true lines collect, then we say that it's our real image. But sometimes our non-real lines like this, which are just continuation, hypothetical, then this image would be our virtual image. This would be the image that we cannot touch or interact with. Yeah, right? We just can't see it, and that's it. Okay, one more formula, which is the magnification. Yeah, magnification, as I have told you, it might be something that gets larger or shorter, but also it tells us about its orientation, if it's upright or inverted. Yeah, magnification has such kind of formula. It is minus di divided by do. So it must be negative from the formula. Okay, and then you have distance of image. This must be up, and distance of the object has to be on downside. And also, what is this hi and ho? Basically, it's just the height of the object. Yeah, it might be, for example, 2 centimeters, let's say, and this thing, for example, let's say it's just half. This height might be just 1 centimeter. So we say that it got shorter twice. Yeah, and why? Because if image is shorter, for example, if it's 1 centimeter and object is not this one, image height, if it was 1 centimeter and object was 2 centimeters, then definitely our magnification would be just 0.5, which is less than 1. And that's pretty good because it definitely tells us that our object just demagnified. Okay, yeah. So let's go back to this one. If the object is magnified, its value must be larger than 1. It does not have to be positive, negative, does not matter. The number itself has to be larger than 1. Okay. When we talk about demagnified, it does not matter minus, positive. No, it's not mathematical thing. Okay. When we say -1, it does not mean that it's just less than 0.5 or something like that. The number itself tells us, for example, 0.5. It just tells us that it got shorter. Okay, if it's positive 0.5, if it's negative 0.5, anyway, it got shorter. Anyway, minus and positive signs, yeah, they only tell us about if the image is upright or inverted. Okay, if you have your magnification at the end being positive number, then it's your image is upright. If you find that your image, your magnification, this m, became negative, then it's inverted. Your object was like this, then your image appeared to be like this. Okay, okay. I hope you understand it. Okay, geometric proof of thin lens and magnification formulas. Okay. Let's look at this. For example, let's say that we do some experiment with this kind of lens. Let's imagine that we are in, I don't know, maybe some 1800s, maybe in 1600s, yeah, or better to say 1700s. And when we do our experiment, we have our object in some distance, this DO, and also we can see that our image appears in some DI. Okay, we give them the meanings, this thing, distance of the object, it would be called DO, this thing would be called DI, yeah, and also lenses have their own focal points. Well, definitely we know that. Then we start to try to understand why is it so, right? So when we draw lines, we apply the same rules like this. Also, we have third line, which is like this, but lines from the center, they do not bend, but we don't need that right now because, as I have told you, we just need 2 lines to cross. The third one will automatically cross with those 2. Okay, we define it as the height of the object. Yeah, this is just definition of it, and this is height of the image. Okay, pretty intuitive. Okay, good. But let's work with these angles. For example, let's say it has some angle alpha. Then this one is also angle alpha, right? Because this is just straight line, and this is straight line. This one is also straight line. Definitely, if this is alpha, this is also alpha. The very same thing goes here, but it's not alpha, it's beta. This is different angle, right? Because you can see that this triangle is not the same thing as this triangle. Yeah, you can see that this is definitely shorter. This is definitely longer. That's why those two cannot be the same angle. Okay. If we do tangents, yeah, we can see here that we have 2 more things. For example, this kind of triangle and this kind of triangle. We can apply the relation between those 2 triangles, which is tangent alpha can be considered as what? Tangent alpha can be considered as HO plus HI divided by DO. Why? Because this upside, it must be opposite. Downside, it must be adjacent. And when we talk about the opposite, in this case, in this entire case, yeah, we take both this part, which is our HO, you can see it here, and also we need to take into account this part, which is this one, which is HI. So we need to take all this part, it's just HO plus HI, okay? And our adjacent part would be this part, which is our D, which is DO, okay? Okay, good. And we can take this small triangle. This part we definitely know it's HI, and also this part is F, and that's exactly what is written here. And we can take also this smaller triangle like this, in fact, and this thing would be our HO. You can see it here, right? And also the downside would be DO minus F. Why? Because we have this distance of F, but we need this distance, and this distance would be the totality, which is DO minus this F part, and that's why we would have something like this. The very same procedure goes for beta. I will not prove it. You can see it and do it yourself. And then just simple mathematics, yeah, just simple mathematics. For example, what did we do? We just took this thing and put here. We took this thing and put here. And if this thing is equal to this thing, right, we can write it here. If this thing is equal to this thing, then we can write it here. And then we do just simple mathematics, yeah, right? The common factor of F, now multiply this by DI, multiply this by DO, then you can see that this is common factor like this one, they go out, and in both sides you can see that HI plus HO, we can cancel these out, you have only 1 divided by F, you have this thing, right? Okay, you can divide by, well, at the top you can have this DI plus DO, at the bottom you have this DI multiplied by DO, and if you divide this thing to each one of them, yeah, like this that I did, yeah, already, then you definitely can cancel one of those out, and you definitely have this formula, which is 1 divided by f equals 1 divided by do plus 1 divided by di. This is a geometric proof of this formula. And when we come here, we're just trying to find the relation between two formulas. Yeah. Again, one of those formulas is this one. Yeah, this one. We are trying to find the relation between this one, and it's also here. It also is here. And if they are equal to this thing and this thing, we can put them again here, right? Okay. Yeah. We cancel these two out together. We cancel these f's together. Then you can see that here we have di, which goes upward, and this di, do, and you can see that this would be hi and ho. Okay. But if the image is inverted, as you can see, yeah, image is inverted, we just write it as something less than 0. It's just minus number. Well, minus is here, and then you can move that minus to the other side. You will definitely have this di divided by do, and then we will define it as our magnification. Okay, good. Okay. Right now, let's try to learn how to draw the ray tracing in different kind of situations. For example, here we have converging lens in 3 different situations, which one of them is the object is behind the focal point, and the second is that object is exactly at the focal point, and that it is in front of the focal point. So it's between the focal point, this one, and the lens. Yeah, it stands between them. The very same thing we're going to do for diverging lens, the same thing we're going to do for concave mirror, the same thing we're going to do for convex mirror. Okay, let's start. Basically, we had this already, but let's do it one more time with you so you understand better. Let me choose some yellow, and we draw lines using those 3 rules. The line which goes straight like this, it passes through focal point. It passes through focal point like this, maybe. Yeah. The line which passes through focal point, maybe like this, it would go straight. Yep. Let's continue this line. Maybe here. Okay, and you can see that we have already here a cross. Then we definitely know that the third line has to, it does not have any choice. The line which goes straight to the center, it does not bend at all, it just goes through. And you can see that it's almost there. Yeah, it's almost there. These 3 lines cross here, then definitely it would be, our image would be something like this. Okay, let's try to solve problem on that. We have this formula, and let's count each of the boxes as 10 centimeters maybe. That's why our do, yeah, our distance of the image, which is this one, would be 50 centimeters. This focal length would be 30 centimeters. And let's say that at the beginning we don't draw this, we just try to solve the problem and see if it matches our image. Okay, if we apply this formula, it would be something like this: 1 divided by f. Okay, we have this formula which is just right here, and we need to find what? We need to find the distance of the image, right? So it would be what? 1 divided by f. 1 divided by do goes there. Both of them are known. We need to find 1 divided by di. Okay, so we need to multiply this part by do. That part we multiply by f, and bottom would be just do multiplied f, right? Okay, this would be 1 divided by di. Then our di would be what? It would be, we just swap it with the bottom and the top. Then it definitely has to be what? This thing has to be dof divided by do minus f. Okay, good. And right now, let's just apply numbers. Distance of the object was 50, focal length was 30. So if it was 50 multiplied 30, this is 50 minus 30, then definitely this thing is 1500. Here we have 20, cancel. Then this thing would be 150 divided by 2, which is 75 centimeters. Our image was meant to be at 75 centimeters. Let's look at this. 3 boxes, 3 more boxes, and 1.5 boxes, which is good. Yeah, this is 30, and 1.5, it's just 15. Yeah, I'm sorry. 15 centimeters. Yeah, it appeared exactly there where we expect it to be, 75. That means that our both ray tracing and our formula, both of them work. What about the magnification? Let's try to find it. We apply this formula of magnification. Basically, we can do what? Let's say at the beginning we don't. Okay, we have this exact height, which is 1 box. It's just 10 centimeters. But let's work with this first formula, which is this minus di. Image would be what? Image would be distance of the image is that 75 that we have just found. 75 centimeters, and distance of the object was 50 centimeters. And if we cancel those out, then this thing has to be what? This is 3 divided by 2. This is about 1.5. Yeah, and centimeter cancel out, because magnification is just a number, how much it increased in size. Yeah, it's not about some unit. Okay, 1.5 means that it just got bigger. Good, it just got bigger. And if it is 1.5, we can also use this formula, the second one, which is hi divided by ho. We have that height of the object, then our height of the image would be height of the object multiplied 1.5. Then it would be definitely, if it is 10 multiplied 1.5, our image was meant to be 15 centimeters. Okay, 15 centimeters, and you can definitely see that this is 1 and this is half of the box. It is exactly 10 centimeters. This is 5 centimeters, and this definitely works. This is 15 centimeters. Okay, good. Let's work with this one. object on the F, what would happen if our object would stand exactly on the focal point. Let's draw lines. Yeah, let's continue this. Okay, this principle, the first one, line goes straight, it passes through the focal point like this. Then the second one goes straight and it does not bend. Okay, and the third one, it tries to move from the focal point, but it stands already on the focal point. That's why we just use these two lines. And you can see that there is a problem. You can see that those two lines are parallel, which means that we also know from geometry that parallel lines, they cannot cross, they cannot meet with each other, which means that there would be no image. Okay, let's solve it mathematically. Will we have something like that? Okay, we know that formula. Again, I would not waste time doing all this formula. I would just take this di, yeah, this di. Okay, this di would be, the final formula was do minus f, and it's already known, yeah, our distance of the object and the focal point are the same distance. This is also both focal point and distance of the object. And if I substitute it with, for example, f, this would be f squared. This thing would be f minus f, which means that f squared divided by 0. And if we divide anything by 0, then this thing has to be what? Infinity. Image would go infinitely, yeah? So the image would not appear, okay? Okay, both works, both physically, both mathematically, okay? Good. What would happen if we put image in front of the f, if it stands between those two? Okay, let's continue. The first principle, light goes in like this. Then it passes through the focal point like this. And the line which goes from the center, it does not bend. Okay, maybe like this. And to the focal point straight, we could draw it, but this too would be enough to us. As you can see, it's a problem. It's a little bit problem. Why? What's the problem about it? Well, we can also use the third one, which is this focal point. If you ask me how would we do it, for example, let's, okay, but to not complicate it for right now, let me not draw it. Maybe I will draw it in the next videos when we solve a little bit hard problems. But right now, I don't want you to be confused. But you can see that these two lines are going away from each other. This one goes straight like this one goes like this, for example. And you can see the distance between them, it just gets bigger, 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 and bigger, which means that those two lines just definitely cannot cross. However, what did we say about hypothetical continuation? If we continue it hypothetically like this line goes like this line goes like this, yeah, at a certain point they definitely have to cross. I would draw it like this. Yep, that's good. And this would be valid, in fact, because this is just 2 points. This 2 box, yeah, it's half. The same thing goes there. It's just 3 boxes and it's half of it, so I just used that principle. You can see it, 3 boxes, half of it, 3 boxes, half of it. The same thing goes for that one. It's just 2 boxes, half of it, 2 boxes, and half of it. And definitely it has to appear in this point, which is our image would look like this. It would appear very far from the lens and the same side of the object. We expect it to be here and maybe some inverted. But the problem about it is that it does not appear here, it appears here. And we have some issue with that, and I will tell you what. Let's write down that formula. Yeah, formula. Okay, we applied here yellow, blue. Maybe right now let's use, I don't know, maybe orange, let's again apply this DI formula, which is DO minus F. Okay, what is the DO? DO, distance of the object, is 20 centimeters, 2 boxes, right? Focal length, again, 30 centimeters. Then definitely you can see one interesting thing. This is 20 multiplied 30. Below we have what? 20 minus 30, which means that definitely we're going to have something negative, because the top one is positive, bottom side is negative. Okay, this thing would be what? 600. This thing at the bottom would be minus 10. And if we cancel these two out, then it has to appear minus 60. It would, okay, what does it mean, minus 60? What does it mean? Minus 60 means that it's just 60, basically. You can see it, yeah, 3 boxes right here, and also 3 boxes right here. It definitely is 60, but what does minus mean? Well, in converging lens, we expect the object to be this side, yeah? We expect it to be this side. We expect it to be like this, maybe. But the problem to it is that it's the same side of the object. It does not appear behind the lens, but the same side of the object where it stands. And this image is not real because not real lines intersect, yeah? Okay, good. What kind of conclusion can we do about this? There are situations in converging lens that it can give magnified, it can give some demagnified, right? It can give us real images, it can give us virtual images, and it can give us upright images, and it can give us inverted images. Yeah. The proof to that would be what? Okay. So you can see that this thing is definitely magnified. It's magnified a lot, and if we calculate it, definitely this thing has to be about 3. Yeah, magnification has to be 3. If you calculate it, I would not waste time on it. You can see that it's 1 box, it's 3 boxes. Okay, so also, there are some situations, for example, there might be sometimes that our object just gets smaller than usual, yeah, than the object. Our image might be smaller. It can be demagnified. It can be real, and because this is real race, that's why you can see that it's real object, real image, I'm sorry. And it can be virtual, because you can see here that it's not real lines. This is imaginary lines. That's why it can be virtual image. Also, it can be upright or inverted, and you can see that our image here is upright, and here it is inverted. Okay. Good, good. What about the diverging lines? So let's do it faster than the previous one. Again, we come here, the same principle. Okay, but here it's important to go outward. We run away from the focal point. And we need to do what? The second rule, just it does not bend anyway. It does not matter which type of lens, it just does not bend. Okay, if I draw the third one, yeah, from the focal, then it would, let's work with the far focal point. Okay, this is a little bit problematic. Maybe put it here, and it tries to go here, but it ends about here. Okay, and it goes straight, right? It goes straight. The one which strives to focal point, it just goes straight. Okay, and the problem to it is that you can see that these 3 lines do not intersect with each other. But again, we can apply always this rule about imaginary lines. If I continue these lines from here, yeah, this one, then it would be like this. It runs away from the focal point, right? Definitely. And what about this one? This line, in fact, it seems to us like it tries to come from here. And definitely you can see that they all cross probably in this point. Yeah, this point. I don't know if I have drawn it correctly, but let's try to calculate it and see if our calculations are correct. Again, di, I would not waste time. We have already proven it. This is do minus f. Distance of the object is again 50. But focal point, as I have told you, in diverging lens, they diverge. That's why it would be minus f. This thing would be minus 30, okay? So this thing below, distance of the object is again 50, and minus, this thing is minus 30. Okay, okay. And right now it has what? Minus 1500. This thing is what? This is 80. This is 80. Okay, if we cancel those out, 150 divided by 80, well, it must give us maybe, okay, let me calculate it fast. Let me choose 150 divided by 8. It gives us about 18 minus 18, because we have minus there, 1875, yeah, 75 centimeters. Well, basically it's good. I think that we are pretty close. As you can see that it's not exactly at this 2 boxes point. It's something very close to that, but it's not exactly at that 20 point, okay? It's not 20, it's 18.75, something very close. And I think that our image is pretty good. Again, it works, but the main thing is that this thing has to be virtual lines, okay? What would happen if we work with this one, yeah, with object on the focal point? Well, you can see that if I draw the lines, continual lines like this, it goes straight, then it goes outward from the focal point. The one which goes to the center does not bend at all. The next one is that the one which strives to the focal, it goes straight. Yeah, okay. If I continue lines like this, it goes away from the focal point, and this one seems to us like that it comes from this point. They all cross probably here. Yeah, this one. And let's try to calculate it again, these numbers, this formula, and let me write it maybe like this. do for my d distance of object would be the same as f, so it is 30. This is again 30, but we need to remember that this thing is minus 30. This is important. For distance of the object is 30 minus also minus 30, okay? So this thing would be minus 900. This thing would be positive 60. So it's just cancel. This thing has to be minus 15. And as our object and focal lengths are 30, it's exactly at the half. This is 15, this is 30. Okay, this is exactly at the half, and it works still. The last situation, let's work with before the focal point, and if we go like this, okay, okay, I'm sorry, it's not converging lens. It must go outward. It must run away from the focal point. The one which tries to go here, it must be somewhere here, maybe go straight. And the one which goes from the center, it must not bend at all, okay? And if I draw some imaginary lines to the focal, well, it would look maybe something like this, and this line would seem to us like it comes from here. So I would expect my image to be somewhere here. Okay, if we calculate it again, distance of the object, distance of the image, I'm sorry, we're working with image, distance of the object is 20. We need to remember that. This is multiplied minus 30. Please never forget that diverging lens has negative focal length. This thing is what? This is 20 minus by the formula, but it is also minus 30, so it will be minus 500 or 600. I'm sorry, this is negative 600, and this thing would be 50. This thing would be 50, and if we cancel, 60 divided by 5 is definitely minus 12. This thing has to be minus 12 centimeters. And is it? Well, yeah, pretty good. It's not exactly at the half, but it's a little bit closer to this 10 point. Maybe a little bit to the right would be correct. Maybe it would be something like this is better. Yeah, and I think that right now it's way better. It seems like 12. Okay. I would not do the calculation of magnification because you definitely know how to do it. You have found DI, you have DO. You just apply it all the time. You would do it yourself to not waste time. But there is one very important thing. If you look at these situations, let's concentrate on them. The first image is demagnified. As you can see, it's smaller than the actual object. This is created by non-real lines, and also it's upright. Yeah, it's not inverted like this. Okay, the second one, it's also demagnified. It's smaller than the actual object, not real lines, upright. What about this one? Again, smaller than the actual object, not real lines, and it's also upright, okay? Which means that, let's write here some rule, maybe with green, I think. The rule would be next. Diverging lens, always, at any case, gives us the magnified, smaller, the magnified, upright, virtual image. So it cannot give us real image, it cannot give us inverted image, and it cannot give us magnified image. It would always be these three things. It would give us definitely upright, virtual, the magnified image. Okay, last two are concave and convex. Then we would have some break. That would be good. So again, this rules again. Here we go. Concave mirror, the mirror which collects light. The very same principle as converging lens, but it's mirror. That's why the light would not go there, and you don't see here focal point. Instead, the light would converge back. It would reflect back. Okay, like this. The one which passes through focal point. Which passes through focal point like this maybe. It goes straight. And let me put it maybe here. Okay, let me continue this line. This would be maybe like this. Okay, and the third one, if it came at some certain angle, it would go the same angle. So if it's like this, then it would be, definitely this one. So all those three cross at some point, which is this one. Okay. As you can see already, it's real lines. It's just real image. It's inverted, and it's magnified because it's, as you can see already, it's larger than the actual object. But let's prove it mathematically. We have this formula. Again, we'd write what? Di equals DOF equals divided by DO minus F. Distance of the image is 50. Focal point is our positive because it collects light. It's 30. And below we will have distance of the object minus, this is 50 minus 30, then it would be 1500 again. It would be 20 minus, and this thing has to be again 75 centimeters. Okay, and right now it would not be just minus, because why? It's exactly there where we expect it to be. We don't expect it to be this side because it's mirrored basically. It's mirrored, it reflects, and that's why this thing has to be positive. We don't care that it's the same side as our object. For lenses, we said that we expect to be other side, right? Because the lines must pass through and they must cross there. But here, we expect our object to be reflected and be the same side as our object. That's why there is no problem. This thing would not be negative. This thing would be positive, right? 75, let's see. And I think that is pretty good. Maybe a little bit to this point, maybe a bit mistake. But the main principle is understandable. This whole distance is just it's just 50. And as you can see here, we have 20, and here a small half, which is 5. This is whole 75. And let's calculate magnification just for this one. Then we will not do it. Minus DIDO. Okay, this is minus 75. This is 50, and this would be minus, cancel. This would be 3 divided by 2, minus 1.5. And this is a really good one. Why? Because, as I have told you, minus 1.5 is not about that it shrinked to that stage. No, instead, 1.5 means that it's 1.5 times larger. Yeah, you can see that it's just 1, but it's 1.5. It's just larger. Okay, then also we can say what? Minus means that it is inverted, and it is. Yeah, we can apply this to the second formula, which is just h of the image divided by h of the object. Then h of the image would be h object multiplied 1. Okay, multiplied minus 1.5, and then image, this would be 10 centimeters. Why? Because we have here, as you can see, one box which is 10 centimeters. 10 multiplied 1 minus 1.5. Okay, and this thing would be minus 15 centimeters, and it's pretty logical. It's okay that it is minus. It only means that our 15 centimeter image is just inverted, and that's it. It does not mean anything else. Okay, good. Okay, what if object stands exactly on the focal point? Then the line which goes straight goes through the focal point. Light which goes some angle refracts the same angle. And light which goes through the focal point, and it cannot. And as you can see, those two lines are again parallel, even if we try to continue these lines, for example, like this, they would go infinitely. And I would not do calculations because we have the very same principle just right here. It would be the same thing. Our image would not appear. It would be an infinity. Okay, good. And I wouldn't even calculate it. You can do it yourself. Let's talk about this one. What would happen to the object if it was in front of the F? Okay, it would be something like this. The line which goes, oops, what is going on? The first line which is straight, then it goes through focal point. The one which goes some angle, it goes the same angle, right? You can definitely see it. It's the same as in our converging lens. These two lines will have more and more distance. That's why let's continue these lines. Yeah, we know that at a certain point those two lines have to meet. Maybe somewhere here, I don't know, but I would hypothetically continue it here. It's just two boxes, which is somewhere. Yeah, exactly correct. It's just here. This is our large object. Okay, as you can see that our image is not real. It's enlarged. It's basically 3 times bigger from the picture, of course, and it is in 60 centimeters distance, of course. Also, it is upright. Okay, let's calculate it and prove if it is so mathematically. Okay, again, orange. Let's write it with orange. DI would be in that. We again have this DOF, DO minus F, and we have what? Distance of the object is just 20, whereas focal point is 30. So this would be 20 multiplied 30, still positive because it's concave mirror, it collects light. This would be 20 minus 30, so we'll have negative number. This would be 600. Here we would have minus 10. Cancel, and you can see that it is minus 60 centimeters, and it's okay. And as I have told you, it is exactly at 60 centimeters distance. But why minus? Because it's not there where we expect it to be. We expect reflected light to be, our image to be the same side, even though it's inverted or not inverted. We just expect it to be the same side as the object because those are reflected. But it would be minus because it's not there where we expect it to be. Okay, if we do just magnification, it would be minus di divided by do, which means that this is minus di is itself minus 60. Okay, and distance of object, which is 20, and this would be positive 3. Okay, and as I have told you, positive 3, negative 3, it does not matter. Plus only means that it is upright, and it is, which means that our calculations are correct. And this 3 means that it is just 3 times larger than the object, and as you can see, it's just one box. The image is 3 boxes. Okay, last thing that we're going to work with is the convex mirror, and let's work with this, and then let's have a break, of course. Yeah. Okay, our image is in, again, 50 centimeters. Its focal point is here. You know that the line goes straight, and then it goes away, maybe like this. It goes away. Why? Because we just continue lines somewhere here. We just imagine to be here, okay? The one which goes straight to the center, it reflects the same angle. So it must be something like this. We can also strive to focal point, yeah? Strive to focal point. This one, oops, I'm sorry. I don't know why it does something like this. Okay, it strives here, but we definitely know that it would be reflected back at probably maybe this point, and then it would be reflected straight. So it works again here as well, okay? Okay, let's draw, okay, hypothetically, if my eye would be here, right? I would think, for example, if I don't know that here we have some object and so on, I would think that originally this light comes from, okay, maybe not like this too much, sorry. Yeah, I would think that object is coming from here. Maybe here we have some object and something like that, right? I would think that our object stands here because the lines, I would think that my brain loves to just continue the image. And the same thing, if my eye would be somewhere here, yeah, this would be my eye, then I would think that this line is originally coming from here. Okay, so the last image would be here. Okay, let's try to calculate it and see if our calculations is correct. If it is not, then we'll correct our image. Okay. Again, this formula, di equals DOF. This is DO minus F. Distance of the object is 50. That is negative 30. Negative 30, yeah, as I have told you, the convex mirror. I'm so sorry. Convex mirror. It diverges outwards. That's why it must be minus. This thing, distance of the object is what? Distance of the object is 50. That is 30. Negative 30. This is 50 multiplied negative 30. Here we have 50 minus 30. Okay. So at the top we have minus 1500. At the bottom we have 80. And this thing would be cancel again. And we have already solved this kind of problem. It was about minus 1875. Right? Do you remember it? Okay. It was probably where it was here, I believe. Yeah, this one. Yeah, minus 18.75. The very same thing goes here because they play almost the same role. So distance of the image is this one. And it's pretty good. It is minus because, again, we expect image to be the same side as it is reflected, but it is not the same side. It's the other side of the mirror. That's why, and you can see that it's very close to that 2-box point, but it is not exactly at that point. That's why our 18.75 works. That's good. The image is correct, in fact, even though we have drawn those virtual lines with our bare hands. Okay. The next one is from the center. Okay. For magnification, definitely you can see that it's smaller. But if you want to calculate, of course, we can. It would be just magnification is minus di divided by do. Our di itself is negative. It would be 75 here, and this thing, distance of the object, is just 50. And we would have some number, some positive number, because minus and minus. If I calculate it right now, give me just one moment. 18.75 divided by 50. This would be 0.375, which means that it has shrinked probably 3 times. It's 3 times smaller, almost, let's say. Yeah, maybe not 3 times, a little bit bigger than 3 times smaller, but almost there, okay? And positive does not mean that it got bigger. Positive, it means only that it's upright image, okay? Good. And it works. Both of the logics are correct. It means that we're in the correct direction. Okay, let's work with this one. It goes straight. Let me put it a little bit higher. It goes, oops, it's not diverging lens, it's convex mirror. It goes out. The one which strives to the focal point, it's just must be here, and then it goes straight. And the one which just goes to the center, it must be reflected the same angle. Okay, if we just continue it again, I would think that it's just here. The source of this, the source of it, I would think it would be somewhere maybe here, and the source of it might think that it is here. Okay, as I see it, it's exactly at the half. It's just 15. I'll expect it to be 15 just based on the boxes. But if I calculate it fast, it would be, again, that formula, di equals DOF, DO minus F. This is 30. This is minus 30. This is important. This is diverging. This is convex mirror. Okay, this is 30 minus 30. Okay, you can see that this thing is what? This thing is just minus 900. This thing below is just positive 60. Cancel, and it would be minus 15 centimeters. 15 centimeters. Okay, 15 centimeters is good, and minus only means that this is 15, and minus is that we expect object to be this 15, but it's minus 15 because it's other side. It's not there where we expect it to be. Okay, we expect it to be here, but it appeared here. Okay, good. It works. And it's exactly the half of the size, as you can see. And if we do it, well, basically you can notice that it's just minus di do. It's just minus di, just minus 15. This is 30, and minus gives us plus. This thing would be 15 divided by 30. It's just 1 divided by 2. And magnification means it's just half of the size. Yeah, it definitely is. The last thing for today is that object is in front of the focal point. Well, you can see that here we don't have focal point, but it's just closer than the focal length, right? Its focal length, if it is 30, you can see it's not in front of the focal point, the same thing. It's not at the focal point. Instead, it's the same distance as the focal length, right? Because the focal point is another side of the diverging, of the convex mirror, right? Okay. Here we don't have it. Okay, good, good. Let's apply these rules and then we'll rest. Line goes straight, and then it goes outwards, runs away from the diverging lens. It goes to the center, goes the same angle, like this, and the one which goes to the focal point, yeah, this kind of, it goes straight like this. Okay, if we just continue to draw these lines, this thing would be, yeah, this one would seem to us that it's just here. Okay, let me choose orange. This is our final. Okay, it's something a little bit closer than 15. It's not exactly the half. It's a little bit closer, maybe that 12 as it was before. Maybe I've exaggerated a bit. So let's calculate it for your practice. So again, this formula, DOF, DO minus F. Our DO is 20. F is definitely minus. This is important. Here we have distance of the object, which is 20 minus 30 again. Okay, at the top we have what? Minus 600. Below we have positive 50. Cancel, and it would be minus, this would be minus 12 centimeters, and exactly that thing that I have said, it's a little bit closer than the 15. It's not exactly the half of it, so it's correct. Yeah, this thing is just here. This is 12 centimeters, and it's also minus. As I have said, usual, we expect image to be here, but it's not there. It's the other side, okay? And the last magnification, let's do it, why not? It would be that minus DIDO, minus our DI is minus 12. It would give us positive something, and DO is just 20. And you can see that it would be positive 12, 20, cancel. If we decrease it by 3, it would be 4, it would be 3. This one would be 5. Okay, yep. 3 divided by 5 gives us what? It gives us 0.6. 0.6, yeah, positive 0.6. Positive means that it's upright. 0.6, it means that it is 60% of its original height. Okay, good. I think that that's it for today. It's not hard problems, but it's not even the problems. We're going to solve problems in the other video. It's just a practice so you understand how to apply these principles in different kind of situations. And also, a last thing that I need to remind you, okay, look at this one. Again, in convex mirror, you can see that all the images are not real. They are virtual lines. Yeah, you can see that these lines are virtual. These lines are virtual. And also these lines are virtual. All of the images, this one and this one and this one, all of them are demagnified. They are smaller than the original size. Yeah, this is original objects. These are their small images, and they are all upright, which means that we have another rule, which is probably the same. Instead of writing it, I would just take it and copy it. Copy, and I would paste it right here. There is a rule, not only diverging lens, but also convex mirrors always give, convex mirrors always give us the magnified upright virtual image. This principle works for itself as well. Yeah, and for concave mirror, as you can see, we can have different kind of situations. It might be, as here, it might be magnified or demagnified sometimes. Yeah, it might be real image, as here it's virtual image here. It might be inverted like here or upright like here. So that means that in concave mirror, it can give us any image, any way. Okay, and also let me bring it here. Magnified and magnified, it works as well in here. For concave mirror, it can give us any type of the image. It depends, but for diverging lens and convex mirror, we apply this rule, and it would be something very handy, yeah, because you always know before drawing the lines, you would already know that the image has to be the magnified, upright, and virtual image. And if you didn't have one of those things, then you definitely know that maybe you did some mistake. Yeah, okay, good. That's it for today. I hope it was clear to you. If it was not, you can write me privately. And thanks for your attention. Goodbye.